Imagine you are not a diver. You have no oxygen tank, no wetsuit, no fins. You are a construction worker, and you are about to descend into the riverbed. The chamber around you is made of steel, roughly the size of a 5-story building, and it is sinking, slowly, deliberately, by its own weight, into the mud at the bottom of the East River. Around you, other men grip their tools. The air is thick, not with water, but with pressure. Twice the pressure your lungs have ever known. Your ears ring. Your joints feel dense. The foreman does not look up. Through the walls, you cannot hear the river. You can only feel it, a constant, invisible weight pressing inward from every direction. The steel holds. For now. You are standing on the future foundation of the Brooklyn Bridge. The year is 1871, and nobody, not the engineers above, not the foreman beside you, not the doctors waiting at the surface, can fully explain what this pressure is doing to your body. Every major bridge spanning open water on this planet hides something beneath the waterline, something the engineering textbooks mention briefly and the tour guides never discuss. Today, we go down there. Hit subscribe before we go deeper. This isn't information you stumble on twice. Lock it in, click now. Every bridge you have ever trusted your weight to, every span over a river, a bay, a strait, is anchored to a foundation system so extreme in its construction that it has killed workers, defied earthquake, and in at least one documented case, been improved by a 2,000-year-old recipe that modern chemistry is only now beginning to fully decode. By the end of this investigation, you will understand exactly what is hidden beneath the waterline of the world's most famous bridges. You will know what caisson disease actually is, and why it paralyzed the man who built the Brooklyn Bridge. You will know how a 6.9 magnitude earthquake moved the towers of the Akashi Kaikyo bridge by a full meter during construction, and why the bridge survived anyway. And you will understand why Roman concrete, mixed with volcanic ash and seawater 2 millennia ago, is still outperforming everything modern engineers pour today. The textbooks describe bridge foundations as solved engineering. They are not solved. They are managed, carefully, expensively, and sometimes at enormous human cost. We begin where every foundation begins, not at the surface, but at the bottom. The workers who built the Brooklyn Bridge's foundations were not submerged. They were sealed inside a pressurized steel box on the riverbed, breathing air pumped in at twice the pressure of the surface, excavating mud by hand while the river pressed against the walls around them. That steel box had a name, a caisson. The word comes from the French for large box, and the description is accurate in the most unsettling way possible. A caisson is essentially an upside-down steel or timber box, open at the bottom, lowered onto the riverbed, and pressurized from above to prevent water from flooding in through the base. Workers enter through an airlock at the top, descend a shaft, and emerge into a pressurized working chamber at the bottom, where they dig, by hand and by machine, removing the mud and rock beneath the caisson so that it slowly sinks deeper into the riverbed under its own weight. The principle sounds straightforward. The reality was not. Consider what twice the surface pressure means in physical terms. At sea level, the atmosphere exerts approximately 14.7 pounds of force on every square inch of your body. Inside the Brooklyn Bridge caissons, workers were exposed to pressures approaching 30 to 35 pounds per square inch. Every breath they took delivered nitrogen into their bloodstream at a rate their bodies were not designed to process. Every hour they spent in the chamber was an hour that gas was slowly dissolving into their tissues. They did not feel it going in. That was the problem. The caisson itself performed exactly as designed. The compressed air held back the water. The mud was excavated. The massive granite foundation blocks were lowered through the shaft and set in place on the riverbed. By any engineering measurement, the system worked. But the men inside it were being changed, at a cellular level, in ways that no instrument of the 1870s could detect or measure. The Brooklyn Bridge's 2 caissons, one for the Manhattan Tower, one for the Brooklyn Tower, were among the largest pressurized work environments ever constructed at that point in human history. The Manhattan caisson alone measured 102 feet by 168 feet at its base. Inside, the working chamber ceiling was just 9.5 feet high. Hundreds of men worked in rotating shifts, in near darkness, in air that smelled of damp wood and pressurized earth. excavating a riverbed that had never seen daylight. What they were building would last over 140 years. What it was doing to them would take decades to understand. The answer turned out to be hiding, not in the mud they dug, but in the air they breathed. And that discovery, when it finally arrived, would rewrite the medical understanding of pressure, the human body, and what we ask of the people who build the things we take for granted. But the caisson held, the foundation set, the towers rose, the men came up, and then some of them could not walk. Between 1870 and 1872, over 100 workers building the Brooklyn Bridge's foundations came up from the caissons unable to walk, joints locked, limbs paralyzed, some of them dead within hours of reaching the surface. The symptoms were not subtle. Men who had descended into the caissons healthy and strong emerged bent double, clutching their knees, their hips, their elbows. Some recovered after a few hours of rest. Others did not recover at all. At least 3 workers died directly from what they experienced coming out of the caissons. Dozens more suffered permanent damage to their joints, their nervous systems, their vision. The medical community of the 1870s had no framework for what they were seeing. The dominant theories ranged from cold drafts in the working chamber to moral weakness, an unwillingness to push through discomfort. Workers were told to walk it off. Some were accused of malingering. Stop and consider what that means. Men were being permanently disabled by a physiological process that their employers could not name, their doctors could not diagnose, and their foremen dismissed as character failure. Washington Roebling, the engineer who had taken over the Brooklyn Bridge project after his father, John Roebling's death from tetanus, descended into the caissons himself, repeatedly to oversee the work firsthand. He was 33 years old. He was, by every account, in excellent health. He came up from the caissons in 1872, unable to move without severe pain. His vision was affected. His ability to walk was permanently compromised. For the remaining 11 years of the Brooklyn Bridge's construction, Washington Roebling directed the work from a chair positioned at the window of his Brooklyn Heights apartment, watching through a telescope as the bridge rose above the river he could no longer visit. He lived until 1926. He never fully recovered. What was happening inside the caissons, and inside the bodies of the men who worked in them, was a process that physics describes with elegant simplicity and the human body experiences as catastrophe. When you breathe compressed air, nitrogen dissolves into your blood and tissues at a rate proportional to the surrounding pressure. As long as the pressure remains constant, the nitrogen stays dissolved, invisible, unfelt, apparently harmless. The danger arrives on the way up. When pressure drops too quickly, when a worker ascends from a high-pressure environment to the surface without allowing the dissolved nitrogen time to exit the body slowly through normal respiration, the gas comes out of solution, not as a gradual release, as bubbles, forming inside the bloodstream, inside joint fluid, inside the spinal cord, inside the brain. The condition would eventually be named decompression sickness. At the time, workers called it the bends, because the pain in the joints forced victims into a hunched, bent posture that was grotesquely similar to the fashionable aristocratic walk of the era. The name stuck. The condition it described was, in effect, the human body boiling from within. The irony is precise and merciless. The same compressed air that made the caisson possible, that held back the river and allowed the foundation to be built, was the mechanism destroying the men who used it. The Brooklyn Bridge opened in 1883. It is still in use today, carrying approximately 100,000 vehicles and pedestrians every day. Beneath its 2 towers, sealed in the riverbed mud of the East River, are the caissons. Still there, filled now with concrete, never removed. The men who dug them out are gone. The chambers they excavated are permanent. But the most unsettling part is still ahead, because the next chapter in underwater foundation engineering involves not a disease, but an earthquake. And the earthquake did not destroy the foundation. It moved it. On January 17, 1995, an earthquake struck Kobe, Japan. And when engineers reached the Akashi Kaikyo bridge construction site, they discovered that the 2 main towers had moved. Not collapsed, not cracked, not damaged in any way that a structural inspection could condemn. moved, shifted laterally, relative to each other, by approximately 1 meter. In the space of the 20 seconds, the earthquake's strongest motion lasted. The Akashi Kaikyo Bridge was under construction at the time. Its two main towers, each rising over 280 meters above sea level, anchored in foundations sunk into the floor of the Akashi Strait between Honshu and Awaji Island, had been standing for 2 years. The cables had not yet been strung. The deck had not yet been hung. What the engineers found when they arrived at the site was a structure that had survived a 6.9 magnitude earthquake intact, but was no longer the bridge they had designed. The distance between the two main towers, originally planned at 1,990 meters, had increased by approximately 1 meter. 1 meter. In bridge engineering, 1 meter at that scale is not a rounding error. It is a complete redesign problem. The question that faced the Akashi Kaikyo engineering team in the weeks after the earthquake was not whether the foundation had failed. It had not failed. The question was whether the bridge as designed could still be built, and if not, what would have to change. What they found when they examined the foundation data was something that the engineers who had specified those foundations had anticipated. Not the earthquake specifically, but the possibility of ground movement at that scale. The caisson foundations of the Akashi Kaikyo towers had been designed with seismic flexibility built into the interface between the caisson and the surrounding rock. Not rigidity, flexibility. Consider the counterintuitive logic of that decision. The instinct in foundation engineering, the instinct that feels correct, that matches common sense, is to anchor as rigidly as possible. Drive the foundation deeper, lock it to bedrock, make it immovable. The engineers of the Akashi Kaikyo did something different. They designed a foundation that could move with the ground within controlled parameters, rather than resist ground movement absolutely. The result was a foundation that survived the Great Hanshin earthquake, one of the most destructive seismic events in Japanese history, which killed over 6,400 people and destroyed over 100,000 buildings in Kobe, without a single structural failure. The bridge that opened in 1998 is not the bridge that was designed in 1988. The main span was recalculated, the cable geometry was adjusted, the deck design was modified. Every change traced back to 1 meter of lateral movement in the foundations. Movement the foundations were designed to survive. The Akashi Kaikyo Bridge is currently the longest suspension bridge in the world. Its main span stretches 1,991 meters. 1 meter longer than originally planned because an earthquake rewrote the engineering during construction. But the most unsettling part is still ahead, because the challenge of the Akashi Kaikyo was bedrock that moved. The challenge of the next generation of bridges is something far less predictable. Bedrock that isn't there at all. The Shenzhen-Zhongshan Bridge, completed in 2024, required engineers to drive foundation tubes into a seabed that behaves less like solid ground and more like a slow-moving fluid. The Pearl River Delta, where the bridge crosses between Shenzhen and Zhongshan in southern China, is underlaid by deep deposits of marine silt, fine-grained, water-saturated sediment that has accumulated over thousands of years at the river's mouth. It does not behave like rock. It does not behave like sand. Under load, it deforms slowly and continuously, a process engineers call consolidation, meaning that a foundation driven into it will, over years and decades, settle unevenly as the silt compresses beneath it. The solution that the Shenzhen-Zhongshan engineers employed was not to find bedrock. In that location, bedrock lies too deep to be economically reached. Instead, they drove steel pipe piles, tubes up to 2 meters in diameter and over 100 meters in length, into the silt in massive clusters beneath each foundation cap. The piles do not reach bedrock. They do not need to. They work by a different principle entirely: lateral friction. When a pile is driven deep into soil, the entire surface area of that pile, not just its tip, but every inch of its length, creates friction against the surrounding material. Multiply that friction across dozens of piles in a cluster, and the cumulative resistance to downward movement becomes greater than the load the foundation must carry. The foundation is held not by what it sits on, but by what it grips. This is not intuitive. It feels wrong. We trust what sits on something solid, not what holds on through friction and mud. And yet, friction and mud is what holds up some of the longest bridges on Earth. The Hong Kong-Zhuhai-Macau Bridge, completed in 2018 and stretching 55 kilometers across open water, used a related set of solutions with an added challenge. The foundations had to be positioned with millimeter precision in open water with strong tidal currents, and they had to be prevented from drifting during the months between initial placement and final securing. Chinese engineers used laser telemetry systems and robotics to monitor and correct foundation position in real time during construction, a level of precision that would have been physically impossible as recently as 20 years ago. But the most unexpected material in this entire investigation is not modern, it is ancient. In 2017, a team of researchers from the University of California, Berkeley, published an analysis of Roman marine concrete, the material used to build harbor structures across the Mediterranean more than 2,000 years ago. What they found contradicted 2 centuries of assumption about why Roman concrete had survived so long in seawater environments where modern Portland cement fails within decades. Roman engineers mixed their concrete using volcanic ash, specifically a material called pozzolana, quarried near the town of Pozzuoli in southern Italy. When seawater infiltrated cracks in Roman concrete structures, it reacted with the volcanic ash to form new crystalline mineral structures, a mineral called tobermarite. That actually filled the cracks and strengthened the concrete over time. The seawater was not destroying the Roman concrete, it was completing it. Modern Portland cement, by contrast, leaches calcium into seawater, weakening at the chemical interfaces where water and concrete meet. The material we currently use for underwater foundations is chemically less stable in the long term than a recipe mixed in the 1st century AD. The answer turned out to be volcanic ash and patience. But that discovery raised an even larger question. If Roman concrete improves with seawater exposure over centuries, what does that mean for the foundations we are pouring today? And the bridges that will still be standing when no one alive remembers who built them? The thread connecting all of it, caissons, caisson disease, the Akashi earthquake, friction piles, Roman concrete, is a single principle that took engineers roughly 150 years to articulate clearly. Stability in underwater foundation engineering is not resistance. It is negotiation. Every breakthrough in this field arrived when an engineer stopped trying to overpower the environment and started trying to work within its rules. The caisson used pressure to balance pressure, not to eliminate it. The Akashi Kaikyo foundations flexed with the earthquake rather than resist it. Friction piles used the soil's own cohesion as their structural mechanism. Roman concrete let seawater complete the chemical reaction that surface curing could not finish. The dangerous assumption, the one that produced the most failures, the most deaths, the most expensive repairs, was always the intuitive one, that a foundation should be immovable, that stability means the absence of movement, that more resistance equals more safety. The history of underwater bridge foundations is, in this sense, a slow education in the difference between strength and rigidity. Rigidity fractures. Strength flexes, redistributes, absorbs. Consider what this means beyond engineering. We have spent over a century building our most permanent structures on the principle that permanence requires immovability, and the evidence, accumulated in mud and seawater and earthquake data, suggests the opposite. The longest-lasting foundations are the ones that were designed to respond. The Brooklyn Bridge's caissons are still in the riverbed. The Akashi Kaikyo's towers are 1 meter further apart than their designers planned, and the bridge is stronger for having survived what moved them. The Roman harbor at Caesarea Maritima has been underwater for 2,000 years and is still mineralizing. What does not move breaks. What moves within design endures. Every foundation hidden beneath the waterline of every bridge you have ever crossed is not a fixed point holding something up. It is a system in constant slow dialogue with pressure, chemistry, and movement, designed not to win against those forces, but to last within them. What this says about us is worth sitting with. We build the most permanent things we can imagine, bridges meant to outlast their builders by centuries. And the secret to their survival is that they were never truly fixed. They were built to absorb what we could not predict. The next time you stand on a bridge over open water, look down. Somewhere beneath the surface, beneath the mud, beneath the pressure and the dark, there is a foundation breathing with the earth, moving in fractions of millimeters, gripping through friction, hardening through chemistry, surviving through flexibility. The water is not being defeated, it is being answered. The strongest things we build are the ones that know how to give. Every mystery we uncovered today leads somewhere deeper. Subscribe, the next investigation is already in progress.